Hello and welcome. If you're new to this channel, can you please subscribe, hit the like and subscribe button to show support, right? So in this video, I will be solving a couple of problems for Newton's laws. So it's forces and Newton's laws of motion. So if you watch this video, you'll see that we'll be solving a couple of problems and then you will be able to apply most of these ideas in the exams, right? So let's get straight into the first question, right? So the first question here, we having we're having two blocks of masses 2 kg and 5 kg, right, connected by means of a light inextensible string, right? We see that, and then the blocks are pulled along a horizontal rough surface, right? So the surface here, it's rough, right? So the fact that the surface is rough tells us that there is friction. These blocks, as they move, they're experiencing friction force, right? So the force makes an angle. We see the force there, which is this force F, right? It makes an angle of 20 degrees with the horizontal, right? So refer to the diagram below, right? So the 2 kg block, we have to read this, the 2 kg block and the 5 kg block experience the kinetic forces, the kinetic frictional forces of 10 and 15 newtons, right? So respectively, right? So what this mean here is that you would imagine Fk for the 2 kg block having to be 10, and the Fk having to be 10 newtons, and then the Fk for this one having to be 15 newtons. So that's what it means. So this one corresponds to this, and then this one corresponds to the 15, right? So I think that's perfectly fine. We will not have much stress with that. So I want us to go and take a look at this diagram. This is a horizontal surface, right? Having a horizontal surface, it means that we can deal with the situation very much easily without having to stress about an incline, right? Like if maybe we had an incline, right? So let's draw the free body diagrams for both situations, right? But for now, I just want us to quickly take a look at how to state Newton's second law of motion in weights, right? So question 2 here, they want us to state Newton's second law. So this is question 2. So 2.1.1, we have to state Newton's second law of motion in weights, right? So we can state it. It states that when the net force acts on an object, the object will accelerate in the direction. Sorry, I wrote acceleration. It's a mistake there. The object will accelerate in the direction, right? In the direction of the net force. And now, so this is the most important statement of the law, right? You talk about when this net force acts on an object, right? And then you talk about what happens, right? The object will accelerate in the direction of the net force, right? And if you take a look at it, the acceleration now, you have to talk more about the acceleration. So this acceleration now is directly proportional, right? So if we take a look at the formula, F net is equal to ma, right? So we divide this by m, both sides. I think you will see mathematically, right, that the relationship between the acceleration, it's F net over m, right? So the acceleration here, it's directly proportional to the net force, right? You have to mention this. So the acceleration is directly proportional. It's directly proportional to the net force and inversely proportional to the mass, right? So we can see that here, according to the relationship, the acceleration is inversely proportional to the mass, right? So the acceleration is directly proportional to the net force and inversely proportional. Inversely proportional to the mass, right? And remember, the mass, this is the mass of the object, right? The mass of the object, right? So I think that's perfectly fine there with the law, and I trust that you will be able to remember and state this correctly to get your 2 marks, right? So this here, it came from it's a result of this formula here, which is the F net equal to ma, right? So I think you will make a way to remember the how to state the Newton's second law of motion in weights, right? So let's take a look at the 2.1.2. So with 2.1.2, like I said, remember, in this video, I will not necessarily be looking at solving the problems, but I will be focusing more on giving you guys as many ideas as possible, right? So what we will do here is I want us to draw the free body diagram of the 2 kg block and the 5 kg block, right? So I see that here they're looking for the 5 kg block specifically, right? So if you are in an examination, obviously you have to draw for the 5 kg block only, not for both, right? But I want us to draw the free body diagram for both of them, right? So the first force that we should not fail on the 2 kg block, there's what is called gravity, Fg, right? And there's going to be the normal force going up, because the motion here, it's towards right, so the friction force, it's most likely to be going to the opposite direction, which is the left hand side, right? So it's going to be Fk, and then here we're going to have the tension. So when you see a rope there, you can do like this. So it shows you that this other part on the left hand side, it's having its tension going to the to that direction, and this side we're having gravity. So this is tension T, right? Here we're having gravity, then we're also having the normal force, then we do have the tension, as you can see here, that it's going in the left direction, right? So this is tension T, right? Because it's the same rope, then it's the same tension between the blocks, right? So here we can have the force, right, being applied at some angle. So we can say this is force F, and then we have that. But remember, we also have the frictional force here of this 5 kg block, right? So I think as a result, we've got 5 forces there, right? We can indicate here that this is 20 degrees, right? So now I want us to draw the free body diagram for the 2 kg block and the 5 kg block. So the free body diagram for the 2 kg block looks more like this. So this is the normal force going up, right? And we're gonna have the gravitational force, which is Fg, right? And then now we would have the frictional force, which is Fk, and we will also have the tension pulling to the right hand side of the 2 kg block, right? So now let's take a look at the 5 kg block here. With the 5 kg block, we have a gravitational force going down, right? And the normal force, it's going up, that's a force. And we have another force here, which is the tension force. And we obviously have the kinetic friction, right, of that 5 kg block. Then we do have a force here applied at some angle with the horizontal, and it's force F. So it's applied at some angle 20 degrees with the horizontal, right? So that's what we have over there, and I think we can go down and take a look at the following question there, right? But for this question specifically, it was looking for the 5 kg block, so we would draw only this one, right? So pay attention to which block they want the free body diagram for, right? And I think you would have gotten the full 5 marks there, because you would have indicated all the labels, right? You would have labeled your forces, right? So let's go to 2.1.3, right? So with the 2.1.3, they want us to calculate the magnitude of the force, right? That is, that must be applied at an angle of 20 degrees with the horizontal, right? So we're looking for that, right? We're looking for that force, right? To make the two blocks accelerate at 2 meters per second squared to the right? So what we can do is we can get the F net of both the blocks, right? Or we can get the F net of the 5 kg block, then see what we have, right? So if we do the F net is equal to MA for the block, so what we will see here is you will see that we can even indicate the components here for gravity. So this force here, because it's going at some angle, so some of its component is pulling in this direction, which is called Fx, and the other component is pulling up, which is called Fy, right? So Fx would be F cos, because the angle is adjacent, so you're gonna say F cos 20 degrees. So this one would say F sine 20 degrees, because if we look at it, it would have been opposite, right? So our Fy is here, so it is opposite to that. So I will not necessarily focus more on the trick for this one, but you will look at the relationship between the force, the component of the force, and the angle. If the relationship is adjacent, then you would automatically use hypotenuse side cos 20, cos the angle, and then if it's opposite, then you would use sine, right? But for now, let's not focus more on that, right? So the Fx is going to be that, and the Fy would be that. So now here we want the F net, right? So remember, we have to consider forces that are parallel to the motion, right? So how many forces are parallel to the motion? So the motion is either going to the right or to the left, right? But most likely in this case, we see that the motion is going to the right. The acceleration is towards right, and it was also discussed here, right? That is going to the right. So if it's going to the right, we can take the right direction as positive and the left direction as negative, right? So it means that here the only force that is going to the right, it's Fx and not force F, right? It's Fx, so we're going to subtract Fx with Fk, and then we'll also minus the tension, right, which is equal to MA, right? So what is Fx? Fx is the force F, and then we can say cos 20 degrees minus Fk. What is Fk? The Fk was given for the 5 kg block. What is the Fk? It was, you can go and check on the question there. We saw that it was 15, right? This one was 15, right? So we're just going to put 15 there for the 5 kg block. So it's 15 here. And then minus the tension equal to the object's mass, which is 5 kg, times the 9 times, not 9,8, but the actual acceleration of the block, right? I see students making a mistake and thinking acceleration is 9,8. So obviously this acceleration here is the acceleration of the blocks, so it may not necessarily be 9.8, right? But the acceleration there of the blocks, it's given, it's 2, and it's going to the right. So remember, we're taking right as positive, so everything that's going to the right, it's going to be positive, right? So the acceleration was also substituted to be positive, right? So according to the looks of things here, we're having two unknowns, right? Two unknown variables. So what we will do here is we would try to simplify this as far as possible, right? But because we're looking for the force, you can see that here we can have F cos 20. You can still have F cos 20 here, and then minus 15. We're just trying to simplify this, and then minus t equal to 10, right? So I think you guys can notice here that we have two unknowns, and the moment we have two unknowns is we can try to use some of the information of the other block, right? Or we can use the horizontal components if we do have those. So I think we can try to use that, but in this case I want us to just do the F net for both blocks, right? So let's do the F net for both blocks. So this is the F net for the 5 kg block. That's why the forces that were considered here was of the 5 kg block, right? So let's do F net for the 2 kg block. F net is equal to MA for the 2 kg block. And I think you guys can see that the force on the right here, it's T. It's going to be T minus Fk, right, equal to MA, right? So what is the tension here? It's going to be T minus, what is Fk? Fk is 10, equal to what? Equal to the object's mass, which is just the 2 kg block, times the 2 for the acceleration, right? So here you can see that we're going to have 2 T minus 10 and then with the 4, right? So because we're looking for force F, I think we would have determined the value of the tension here if we transposed the tension that if we transpose the 10 that side. So T is going to be 14 newtons, right? So it means that the tension in the string of those two between that is connecting those two blocks, it's equivalent to a value of 14 newtons, right? So if it's 14 newtons, then it means that because we had two unknowns here, then we can substitute that over there and do some calculations here. So we substitute the 14 here, do some couple of calculations, and then we just simplify this and then get straight to the answer. So what is minus 15 minus 14? It's gonna be, so let me use my calculator here. Hold on for a second. So for that one, it's going to be minus 29, right? So obviously we will have to transpose the answer that side, right? And when we transpose the answer that side, we're gonna have F cos 20 degrees, right, equal to 10 plus 29, right, which is 39. So I'm not going to write that in full, but I'm just going to quickly go down here and divide both sides by cos 20, right? You know what we do. Remember, this is going to be a simple equation to solve, because you know that you have to apply mathematics, right, in order to solve these things and simplify, right? So we know that we're just going to say cos 20 there on the calculator. So, and the value for the force, it's about 41.50, right? So this is the force F, right? And I think we did that perfectly fine there, if we didn't make any mistake, right? And I think I will now go to the next part of the problem. So now we have these things on a different surface, right? So we can still apply the ideas of the two blocks of masses 5 kg and 2 kg are connected by a light inextensible string, right? So a force F is applied on the 5 kg block at an angle of 20 degrees, right, to the horizontal, and the system of blocks accelerate to the right at 2 meters per second squared, as shown in the diagram, right? So the kinetic frictional force of on the 5 kg block is 10 newtons this time around. So you see that the kinetic friction force there is 10 newtons, right? So this one here, it's hanging, so we might not necessarily have friction in there, right? So it's fine, unless maybe they mentioned that the friction was not ignored, the effects of air friction was not ignored, right? So let's take a look at the 5 kg block here in this case, right? So we have possible forces here, like your normal forces, your normal force. So let's have the normal force there, right? Remember, it must be going exactly up. So normal force is there. Here we've got gravity, then here we've got the tension force, right? I said when you see a rope, you can cut it like this, and then it means that here the tension force, it's going to that direction, right? So this is our tension, and when you see a rope here, you can cut like this. So it means that this one, it's a system on its own, right? So it has its tension force pulling it up. So this is T, and then this is FG, right, which is going down, right? So here we're just gonna simply have the force F with its angle, of course, and the frictional force, frictional kinetic force, right, Fk, right? So now let's quickly go into the first question, which is 3.1, right? So for question 3 over here, we can go to 3.1. They want us to define the term normal force, right? So for normal force is just the force that is, you can see it's this force here. It's always perpendicular to the surface, right? And it's being exerted by the surface. So objects that are hanging, they don't necessarily have the normal force. Like the 2 kg block here, we do not have the normal force because it is not in contact with the surface. So how can we define that? We can say a normal force is a force which a surface exerts on an object. On an object in contact consider that it's in contact with right, and you can also talk about the force being perpendicular, and which is perpendicular. So it's always perpendicular to the surface, right? But it is, even though it is exerted by the surface, right? So perpendicular to the surface, right? I think we have it there, and we can move on to 3.2, right? Oh, sorry. Okay, let me charge this quickly. I want us to draw a free body diagram, right? Just to draw a free body diagram of all forces acting on the 5 kg block, right? So how do we do that? Right, remember I said the purpose of these videos is just to give you guys as many ideas as possible, right? But it's not specifically solving the problems, right? But I just want to use this opportunity and discuss some of the most important basics with you guys. So the 2 kg block here, we can draw its free body diagram here, and we will see that the only forces acting here, it's the tension force which is going up, and the gravitational force is going exactly down, right? So here on the 5 kg block, we have the normal force, right? We have a force here called the tension force, right? And here we also have the kinetic frictional force, and we have a perpendicular a force applied at some angle there, which is force F. I don't think we do know its magnitude necessarily, but okay. But the force is being applied at some angle there, right, which is 20 degrees, right? So we're going to also have the gravitational force, which is going exactly down, right? So that's how we would have drawn the free body diagram of the 5 kg block, right? I think you guys understand now what's happening, and we can now move on to the questions for the calculations. So 3.1, the first question just went on straight to say calculate the tension in the string, right? So of course, by the looks of things here, we have two free body diagrams of the blocks, right? And for that one, for that question, remember they said the 5 kg, we would have considered only this one, right? And then we get our 5 marks there, right? So now let's get straight to the to 3.3.1. Calculate the tension in the string, right? The tension in the string, now we can choose which option we use, right? It's either we use the 5 kg block, right? But the 5 kg block has got too many unknowns in there. Sorry, this is force F, right? We've got too many unknowns in there, right? Because we have the force and we have the tension unknown and we have the force F unknown, right? So we can choose to use the 2 kg block, right? So we can do the F net equals MA for the 2 kg block. If we do that, you will see that we'll be taking because this system it's accelerating to the right, right? They said the system is accelerating to the right. It means that this would be accelerating up, right? So as this goes to the right, this is going up. Do you see that? You can have a picture of that. This 5 kg block accelerating to the right and this one accelerating up, right? So we're going to be forced to take the direction of motion as positive. So we're taking the upward direction as positive and that direction as positive, which is the right, and then this one as negative, right? And the opposite direction as negative, right? So should we do that, we would have the tension having to subtract the gravitational force of that, right? And the MA here. So what is the tension here? So the tension is going to be T. We don't know the tension, but we do know what is Fg, right? By definition, Fg, which is the weight, is equal to the mass times the 9.8 gravitational acceleration, right? So what is the mass here? So the Fg is the object's mass, which is 2 kg times 9.8, right? Then on the right hand side, we've got the object's mass and the acceleration, because the acceleration is for the system. Remember, the acceleration of the system was there, and they had said that it's 2 meters per second to the right, right? So now let's quickly go and punch that on our calculator and get the answer, right? So it's going to be 2 times 9.8, right, which will give you 19.6. So this is T 19.6 equal to 4. Then we'll simply transpose this value that side. So the tension value here, it's going to be 4 plus 19.6, right, which gives us a value of 23.6 newtons, right? So I hope you guys understand there, and I think we can freely go to the second question of the calculations there, just 3.3.2. So they're saying now that we have to calculate we have to calculate the force F, right, as shown on the diagram, right? But how can we calculate the magnitude or the size of that force F? I think now we can make use of the 5 kg block, right? What if we do the F net of the 5 kg block? Remember, the 5 kg block, it's there, we have it there, right, with its components, right? So here, because the 5 kg block, it's being applied at some angle, this force would be converted into components, right? So we're gonna have this component Fy and we're gonna have this component Fx. And I think you still remember earlier on in the video we had that this was adjacent, so it's gonna be F cos 20, right? And the Fy, it's gonna be F sine 20 degrees, right? So now let's go and do the F net for the block. So F net is equal to MA, right? So what is the F net here? If we take a look at it, so the F net, it's going to be the component of gravity. So the X component, which is Fx, right? It's going to subtract the tension. It's going to subtract the kinetic friction force and also the tension, right? Which now we would have MA here, right? So what is the Fx? Remember, Fx, we said it's F cos 20 degrees, right? Minus, what is Fk? So the Fk was there. We had calculated, we were given that the Fk for that block was 10 newtons, right? So we'd simply go and substitute minus 10, right? So when we substitute minus 10 here, we also realize that the tension value was calculated. Remember what the T value here in the string, it tells us that it's the same T value for both the blocks, right? Because they are connected by the same string, right? So the tension in the string, it's going to be the same amount, so it's going to be 23.6 as well, right? So what is the object's mass here? The object's mass, it's going to be 5 kg, right? And then times the acceleration. The acceleration was said to be 2, so we can quickly go and calculate that. And I think if we do this properly, we'd see that this is going to be F cos 20 minus 33.6. So let's just confirm that. It's minus 10 minus 23.6. Right, so it's going to be minus 33.6, so this is going to give us 10, and when you transpose this that side, you will see that you'll get 10 plus 33.6. so it will give you the value of the F cos 20. You'll be left with F cos 20 on the left hand side with the 43.6 this side, right? And then if you divide both sides by cos 20, you'll see that the force F will result into 46.40. right? If you round that off properly, I think we got something like 46,398, and if you look at the third digit, we want to round it off. It rounds off the 3 to the 4, and then that's what we're gonna have for the force F, right? So we have calculated the force F, and I think the last question now just wants us to calculate what's called the kinetic friction, the coefficient of kinetic friction, right? Because we do have the mu k here, I think we do have the fk, right? And you know, by definition, fk is equal to ukn. And if you take a look at what they want us to calculate, they want us to calculate this, right? So because we have the 10 newtons here for the friction, do we have the n, the normal force of that object? Remember, the object we are dealing with here is the 5 kg block, right? So we can have the normal force here, then we can have the gravity here, and then we can have the force here, right, with its 20 degrees here, and the tension this side with the frictional kinetic force, right? So I think you guys can see that in this drawing we would possibly have the component fx, right, which is going up, and then the other component is going up. So what is that component? So that component there, it's Fy. It's the y component, right, of gravity. So I hope you guys can see that here. If we wanted to do the F net for this block, we would only consider these forces, right? Forces that are parallel to the motion, right? But we can also make use of forces that are vertical, of the vertical forces, right? But then we know that the vertical forces in this case, since the object is not moving either up or down, but it will be lying on the surface as it moves to the right, right? It means that the forces are balanced. It means that there's what is called F net y, which is actually balanced, right? So F net in the y direction has no acceleration, right, for that for that specific block, right? But that's perfectly fine. Let's not go into much detail with that, right? But rather focus on simplifying this thing, right? We need the normal force. The reason why I'm having all this discussion here is we need the normal force. But you can see that there are two forces going up. I think the normal force and the Fy, they're going up. And what's going down here? It's the force of gravity, right? So if I'm saying that the forces are balanced here, it means that what goes up should be equal to what's going down. So you will see that here the normal force plus the y component is equal to the gravitational force. Do you see that? Because what's going up there for the 5 kg block should be equal to what's going down, right? So if we have that, and if you allow me to transpose that side, right, you would see that the normal force here, it's going to be equal to the gravity minus Fy, right? the gravitational force minus Fy, right? So what is the gravitational force here? The gravitational force is going to be mg minus, and then what is Fy? Fy, remember, it was F sine theta, right, from those components, right? So it means that if you see this kind of a situation here where the object is being pulled up, is being pulled at some angle, right, it's a pulling force, then it means that the normal force would be equal to the weight, right, of that object minus the y component that's going to be contributing towards the upward direction, right? So I hope you can see that, but I'm not going to focus more on that, but I will sort of discuss this with you in the upcoming videos, right? But I hope you guys remember this idea, and if you've been following, you would be able to apply this idea, right? So we have the mass here, which is 5 kg block, which is the 5 kg block 9.8, and then we're going to subtract this with F sine theta, and I think we have the F value, it was 46.40 sine 20, right? So the answer you will get here for the normal force, it's going to be the answer we have to plug in here as we want to calculate the mu value, right, the UK or whatever you call it. So it's going to be 5 times 9.8 minus 46 sine 20 degrees, right? So what is the answer here? The answer is 33.27 newtons, right? I hope you guys understand what I'm talking about here, and we have gotten the normal force here that we have to substitute here. So divide this by the normal force, both sides, so it's 33.27. we would get that the mu k value for that situation, or the mu or the UK, whatever you guys call it, it's just gonna be 0.30, and I think it looks correct, because and the mu k value does not have the SI units, remember, right? Because the newtons here for the FK would cancel with the newtons for the normal force, right? So I think it ranges in between that. I think it should range in between 0 and 1, the mu k value, and I think should you get answers that look like this, they are convincing, like mostly 0.2 and something like that, right? So I think it's perfectly fine with that question, and I hope you guys have learned quite a lot in these two problems that we have done, because I'm trying by all means to discuss and remind you of some of the most important information, right? So I hope you guys are still there, and I hope you guys would like us to do this one right together, right? I hope you would understand. Let's get straight into this one. It's question 4, right? So 2 blocks of masses 1.5 kg and 3.2 kg are connected by a light inextensible string, right? So a 24 Newton force is applied on a system of blocks, right, to move them up an inclined surface, right, which is 25 degrees to the horizontal at a constant velocity, right? The word constant velocity tells you that the velocity will not be changing, so we will not be necessarily having the acceleration. The objects are not accelerating, but they're just moving in uniform motion. So moving in uniform motion means that the forces are balanced, right? Or the forces, the F net, it's just simply equal to 0, right? So let's now get straight into the question, right? But I think we have some information here that is important, as shown on the diagram below, right? So the 1.5 box experiences a constant frictional force that is 2 newtons as it moves up the incline, right? So let's do that one. So question 4 here. Let's take a look at the, I'm not going to state Newton's second law again, right? So I'll simply move on to the 4.2, right? Draw a labeled free body diagram of all forces acting on the 1.5 kg block, right? They say box, they say block. Okay, that's fine. We see that. So now here we will possibly have a force called the gravitational force, right? And perpendicular force is a force that is always perpendicular to the surface. So to look more like that, not necessarily going up, right, but going in that specific direction. And I said to you, if you see the rope, cut it like this, you will see that here the tension would be going in that direction for the block, and the tension will be going down for the 3.2 block. So the normal force is also going in the same direction for this one, right? And this one is going to be FG, right? So never mind the sounds in the background, sorry about that. So here we are going to have the frictional force, just said to be kinetic force, the kinetic force, right? Because I think they did mention that it's a rough surface, right? So we have to see that, right? So they said a 24 Newton force, right? So we see that 24 Newton force. So this is force F. It's 24 newtons, right? Going up. So here we have the tension, and I think we also have the kinetic friction for this one, right? So these are, and I think the gravitational force here, they didn't draw it properly. It's not correct to put it like that. It must go exactly downwards, right? In such a way that we can see the components of gravity, right? So I think that's perfectly fine there, and I think we can draw the labeled free body diagram of the 1.5 block, right? So the 1.5 block, I'm going to draw for both. So the 1.5 block would have gravity going down, and after having gravity going down, it will have the normal force going in that specific direction, and here would have some dotted lines here with the tension going up and the friction going down, right? So this angle here is going to be 20 degrees, right? So we can also have another one here with the tension, with the force F going up. This is the 3.2 kg block. We have the normal force going up like that, and then we have the Fk. So these blocks are moving up the incline. That's why the kinetic friction is going to oppose the motion, right? So we're going to have the Fk there. Then we will also have tension, right? Then here we have the gravity going exactly down, right? And the angle is still 20 degrees. Okay, I think we have the free body diagrams there, and I think for this one specifically, they wanted to see this, right? And you would get your 4 marks there, right? I just hope it's 100% correct. I don't think there's any mistake we did with this, but you guys are just gonna look at it, and then you guys know better, of course. So 4.3.1, right? Calculate the tension in the string connecting the two blocks, right? So we're simply gonna do the Fnet for both blocks, but remember, keep in mind that Fnet is equal to ma. The acceleration is 0, so this part goes on to 0. So the Fnet, it's simply 0 for both the blocks. So let's do Fnet for the 1.5 kg, right? So we'd see that the tension is going to be going up because we're taking up the incline as positive and down as negative. So it's going to be the force F, it's going to be tension, minus Fk, right? Which is equal to 0, right? So what is the tension here? Minus Fk. What is the Fk? I think they did give us the tensions here. They said the tension, the frictional force of the 1.5 it's 2 newtons in the statement there, right? You can see there 2 newtons. So let's substitute 2 newtons there. So the value is 2 newtons. 2 newtons equal to what? To 0, right? So I think this is getting to be a very simple equation to deal with. But then remember, it's not as easy as this with an incline, right? We must consider the component of gravity. Remember, the component of gravity, it contributes to forces that are perpendicular, to forces that are parallel to the motion, right? So like for example here, if you look at it, the gravity is going to have a component here going exactly down, which this component is said to be the perpendicular component. It's perpendicular. We're saying it's perpendicular because it's perpendicular to the surface, right? And it's also going to have another force that is going down the incline, which is called Fg parallel. So you'll see that the 20 degrees is going to be in there, and this is going to be Fg, because it's opposite to that. It's going to be Fg sine 20 degrees, right? Hypotenuse side, which is the Fg cos 20 degrees. So if you don't mind, you can memorize that your Fg parallel, it's Fg sine 20, it's Fg sine theta, and then your perpendicular, it's Fg cos 20, right? So I hope you get it there, and don't forget that Fg by definition is mg, right? So let's calculate the tension, or let's do the Fnet for the block, right? So here we not necessarily gonna have that equal to 0, but we should remember that on an incline always we must consider the Fg parallel, right, being one of the forces to be included in our Fnet equal to ma in our Newton's second law, or Fnet equal to ma for the block, right? Okay, let's now substitute that. So it's going to be the object's mass, which is mg. So this is going to give us mg sine 20, right? So what is mg sine 20? Is the object's mass. The object's mass is 1.5, 9.8, right? And the sine of 20 degrees, right? So what is the answer here? So it's going to be minus 2 minus 1.5 times 9.8 sine 20 degrees. So the answer we get there, it's a negative answer, right? It's negative 7.0276 and stuff, right? If you transpose this that side, you'll get that the tension value, it's going to be 7.02, okay, let's just say 3, right? Round off to that, right? I think this is the answer we got for the tension, right? So now let's move on to the 4.2.3. So 4.3.2, they want us to calculate the coefficient of kinetic friction between the 3.2 block and the surface, right? So there are quite lots of ways you can approach the question, because we can automatically think of Fk UKN, right? But then do we have the n here for the block? So I want you guys to remember something, that the normal force here is equal to the perpendicular component. So the normal force is equal to the perpendicular component of gravity, right? And the perpendicular component of gravity, it's mg cos theta, right? So provided that there are no forces applied at some angle on an incline itself, right, then the normal force gets directly equal to that, right? Can you guys see that there? If I indicate it here with if I'm considering vertical forces here. So considering vertical forces here is only 2 forces, which is the normal force and the perpendicular component, right? So the normal force is equal to the perpendicular component, which is mg cos theta, or mg cos 20 in this case, right? But okay, that's fine. We just realized that on our question here, we do not have the frictional force of the 3.2 block even though the question wants us to calculate the mu k, right? So it's not as easy as the other question we came across here, because on the other questions we had the kinetic friction force, right? So here we do not have that kinetic frictional force of the specific 3.2 block. So what we can do is we can simply make use of the Newton's second law of that block. F net is equal to ma for the block. So let's do F net is equal to ma for the 3.2 block. Right, so when we do F net is equal to ma for the block, what do we have? F net is equal to ma, it's going to be F net is equal to 0, right? Remember? So I see only one force going up there, right, which is force F. So force F is the only force going up, minus the Fk, and minus the tension force, right, which is equal to 0. Remember, we have to also subtract, because this is an incline, we have to subtract the Fg parallel of that specific force, of that specific object or that specific block. So what is the force F? Force F is that 24 Newton that was said to be going up. You can see there on the block, it's over there, 24 newtons, right? So we'd say 24 minus, we don't have the Fk, right? Remember, the goal here is to calculate this, but if we don't have this, it means that we have to work to get that and get the normal force as well, right? Minus tension. What is the tension of the block? The tension of the block was calculated in the previous question. I think it was 7.03, right? Minus, what is Fg parallel? Fg parallel, it's going to be mg sine, right? So what we're talking about now here, this is Fg perpendicular for that block, this is Fg parallel for the block, right? But it is still the same thing. It's going to be mg sine theta, because the 20 degrees is there and it's opposite, right? So it's still mg sine theta. So which is the object's mass? We'll put, because here we're doing for the 3.2 kg block, right, would say 3.2 times 9.8 and then sine 20 degrees, right, which is equal to 0, right? So now let's simplify all this. So it's 24 minus 7.03 minus 3.2 times 9.8 sine 20 degrees. So we have an answer here which is 6.24, right, minus Fk equal to 0, right? So I think if you transpose Fk that side, you'll see that 6.24 would be equal to the Fk, right? So the Fk here in this case is equal to 6.24 newtons, right? So it means that here we can substitute the 6.24 newtons, right, to calculate that, right? So I'd substitute 6.24 and then the mu k. I need the n now. What is the n value? Because this is an inclined, so on an inclined plane, we said that we can, so for normal force in most cases, I think you will have to consider vertical forces of a specific block, right, of a specific block. So we see that here the only vertical forces acting here, what's going up, it's normal force, and what's going down, it's Fg perpendicular. So those two are equal, are directly equal, right? So what's going up is equal to what's going down, right? So if that's the case, you'd see that the normal force is mg cos theta. So in this case here, I would simply go and write that the normal force, it's going to be mg cos theta, right? So the normal force is what? It's the 3.2 times 9.8 and then cos 20. which is the angle of inclination. So let's do that quickly. 3.2 times 9.8 cos 20 degrees. Then I'll get the answer here for the normal force. It's going to be 29.47 newtons, right? So this is going to be 29.47, right? Then we'll divide both sides by 29.47, 29.47, right? So what is the mu k here? The mu k for the block, it's going to be 6.24 divided by the answer, and we'll get the mu k value to be 0.211, right? Roughly that. And I think it's also convincing that it's going to be the answer, provided that everything was done correctly here, all the manipulations of the free body diagrams and everything. But I hope you guys are learning from these problems, and I hope that you will be able to apply most of these ideas, because I see students, they struggle with some of these things here. So I think even though maybe some of the questions here might not be done like at their level best of solving, but I hope you guys are learning, and I think this video might have reminded you of some of the most important basics, right? So I think I'm just gonna simply end this video here, and I hope you're doing good, and bye.